Cool.
A nice big screen.
Have we started?
Welcome to the Digital Amateur Television Experimenters Night. This is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. You realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world. Also participate in the night by coming up to the Queen's Domain club rooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7 OTC.
Okay, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. And I have welcome Rex and Richard to the studio. So VK7MO and VK7ZBX, I think we can both see you, yes, on there. And welcome to the new studio. Now, I've got Rex and Richard in the studio because Rex has been doing some very interesting...
Don't we have a introduction?
We do, but it's not in front of me right at the moment. So
okay.
It's actually over there.
Oh,
So
that's all right.
Richard, can you just grab the bag there? You're spot on, Rex. And
I just thought
that's the page. That's the page, actually.
Let me just...
That's the page. So
I was thinking of the standard introduction that you do with the test scheme and all that sort of stuff.
No. Well, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania. But before I attempt to commence again, I wish to acknowledge Tasmanian Aboriginal people as the traditional owners of the land upon which we meet and pay my respects to elders past, present and emerging, for they hold the memories, the knowledge and the culture and hopes of Aboriginal Tasmania. So thank you for that reminder, Rex. So now, Rex and Richard are in the studio to take us through some experimentation that Rex has been doing with Brodie. And where does Brodie reside?
He's at Wonthaggi, which is southern Victoria.
Okay.
And what we've been doing is some aircraft scatter tests and some tropo scatter at the same, watching for tropo scatter at the same time.
Okay.
And comparing the signal strength of both.
Okay.
Now we'll just have a look in the next slide at the situation between Brodie and I.
I'll just get that up for you, Rex. Just bear with me. Because...
Too many buttons.
Too many buttons, yeah, you're right. Oh, there we go. So... Okay. So, very long title, Rex.
Yes, I couldn't make it any shorter though. I wanted to say all these bands. I wanted to say aircraft scatter and tropo scatter, and using spectrum lamp to find the difference between these two signals.
And a very impressive piece of software, that.
Is it ever? It's wonderful.
So, now, what are we looking at here?
Okay, all these pink lines all over the place are the standard aircraft routes.
Okay.
Now, I have increased the width of the standard aircraft routes that fly between Hobart and Melbourne, just so they're a bit more visible.
Obvious, yeah.
And when they fly from Melbourne to Hobart, they fly down that left-hand route.
Okay.
And
Fairly direct route. So
fairly direct, although they do sometimes turn at Devonport and go straight for Hobart Airport.
Oh, okay. So they do a little angle. Yeah.
But not always.
Okay.
I think the standard route, there's an NDB at the end of that line. They used to always fly between NDBs, but I think they sometimes get permission to do shortcuts using GPS at this stage. But in the middle of the path, which is mainly of our interest, they generally fly pretty close to the standard routes, which are from NDBs located around the place.
Okay.
And as we know, they're getting rid of a lot of the NDBs. So 600 metre people get interested. So we got these two big pink lines showing the aircraft routes, and in the middle is a red line which is the direct line of sight, or the direct path between Brodie and I.
Okay.
Now, to get the best aircraft signal, you need the aircraft to fly right down the red line.
Which it doesn't look like it does that very often.
It doesn't. But it... So you on neither of these situations are we going to get the absolute best signal.
Okay.
But...
On the left one, obviously better.
The left one is certainly better.
Yeah.
But there is another complication which we will look at in the next slide. This is my takeoff at my place, and you can see that if I'm beaming for the Melbourne Hobart flight, I'm pretty close to the top of Mount Knocklofty.
Yes.
And that doesn't cost me much, but it costs about 1 degree, and 1 degree out in the middle of Bass Strait costs you quite a lot.
Yes. In distance.
In distance. And what that means is I can generally copy the signal from Brodie about 100 kilometres north of Devonport.
Okay.
And he can still copy it. His takeoff is actually not obstructed. He just goes straight out over the water at Bass Strait.
Okay, cool.
And he can generally see the aircraft still to somewhere in the middle of Tasmania.
Okay.
Depending very much on whether they start dropping down too quickly.
Yep.
And these distances where you can see the aircraft also depend on what the actual height of the aircraft is.
Yep.
They can fly typically between 33,000 feet sometimes, 39,000 feet other times. That's just whatever.
And you mentioned the 38,000 feet. You had someone...
That's right.
Almost to the other side.
That's right. At 38,000 feet, we'll go on to that later, but basically I can see almost to the bottom of Wilson's Promontory. Not quite, but yes.
Okay. Cool.
So your takeoff angle is very important for this aircraft scatter.
It is.
And the height of the aircraft is very important.
Yeah.
I have put in a little blue line, and that blue line actually gives my takeoff angle almost negative, just a fraction negative.
Okay. Okay.
And I have seen aircraft, the one we talked about,
Yep.
almost to the other side of Bass Strait, when, for funny reasons, the aircraft flew a different path.
Yeah. But and that's a good indication between those the orange and the red line versus the blue line. When you look at it, there's not much
No.
difference, but you're off the side of Knocklofty, so you've got a bit better view of the horizon.
Yes,
That makes all the
it
difference.
probably makes 150 kilometres difference.
There you go.
To where you can see the aircraft.
I love it.
And it's only about 50 feet difference.
Yep. Okay.
Okay, next slide. Now, on 70 centimetres, which is probably the best band to do this stuff,
Okay.
using Spectrum Lab, there's the normal waterfall display on the left, that's sort of dark black to blue,
Yep.
with two lines on it.
Mm.
The dotted rough line is the troposcatter, and
it's straight.
but
And it's straight.
it's straight and it's right on 1,000 hertz,
Okay.
which is the frequency that's being transmitted.
Okay.
The much brighter line is the aircraft scatter, which has been Doppler shifted, in this case probably 4 or 5 hertz, I think.
100 hertz? No, 5.
No, that's 5, yeah, maybe 3 to 4 hertz.
Oh, that's 105. Yeah.
Yes.
1,000 to 1,005. Yep.
Yeah. Now, the nice thing about Spectrum Lab is that it's also got a plotter, like an old chart recorder, multi-pen chart recorder, and you can set up little mathematical functions in it. And if you look at the bottom there under troposcatter,
Yep.
I've set up a little mathematical function to find the peak amplitude between 998 and 1,002 hertz. And as you can see, the troposcatter is all contained within 998 to 1,002.
Yep.
And then to look for the aircraft, I've set it up to look between 1,002 and 1,013. It doesn't matter how far you look, you're looking at the peak amplitude. And you'll see that the red is the troposcatter,
Yep.
and the blue is the aircraft. Now, at the right, you can see the graph of the aircraft versus the troposcatter. Now, there's about 15 dB difference.
That's 15 to 20 dB difference. Well and truly.
As well as that, you can see where the troposcatter's moving around much more rapidly.
Yep.
And that's the nature of troposcatter. You're scattering off little pressure differences due to the little eddies in the troposphere.
Okay.
And sometimes all these little eddies work in phase and sometimes they work out of phase. And so that causes a slight amount of spreading as well,
Yep.
which you can sort of see on the waterfall. Now, to make this work, I have, in this case, Brodie's receiving and I'm transmitting.
Yep.
And I have to transmit just a single tone because I don't want modulation mucking up
Yep.
the results.
Okay.
So what we do in practice, because you can record the data real time on Spectrum Lab,
Yep.
but it's difficult to get the timing right as you can with WSJT.
Right.
And unless I transmitted continuously which I don't want to do, all I do is transmit a single tone every second period on WSJT,
Okay.
and then Brodie can record the WSJT files and then replay them on Spectrum Lab, and that means the timing's all right.
Yeah. Okay.
And so that's the way this works.
Okay.
Now, if we look at the next slide, we'll see the aircraft that produced this, and you can see that red aircraft, which I've highlighted.
Yep.
J something 708.
JS 705. JST 705.
Now, that aircraft had just sort of turned, and I suspect it finished up going direct to Hobart, so it produced a stronger signal at the end of that period.
Okay.
Which, if you go back one, you can see the blue signal got stronger just at the end, at the same time as it appeared to divert off.
Yeah. Okay.
Because it was turning towards the path, you got more faster doppler shift, and it went higher.
Fantastic.
So we go.
Good confirmation.
Yes, we'll go to the next slide. Now this is one where there is, if you look at the waterfall, there's actually 3 aircraft as well as a tropo scatter.
Okay.
Now you can set up as many pens as you like in
Spectrum Lab.
Spectrum Lab. So, but I have set up one called tropo scatter, another aircraft 1 and aircraft 2.
Okay.
In practice, the problem was aircraft. Which one? Aircraft. Aircraft 1 was almost. Well, no, it wasn't aircraft 1. Aircraft. And the third aircraft was almost sitting right on the top of the tropo scatter.
Right, it's that one.
And
Yeah.
I couldn't define the thing accurately enough.
It was mixed in with the tropo scatter signal.
So that aircraft is actually marked as a red graph.
Okay.
And it is, well, it's marked as tropo.
Yep.
The interesting thing is the actual gain on these 3 aircrafts very similar. They're varying out a little bit, but no more than about 5 dB.
Were they all the same sorts of aircraft? From an aircraft profile?
I haven't checked that. I could check it, I guess, but I haven't checked it. I suspect they might have been. One of the things you can tell when you look at the next slide is if they're big aircraft, they show up slightly bigger than...
Yeah, bigger icon.
So I think this aircraft that was... There's 3 aircraft flying up to Melbourne from either Hobart or Launceston.
Yep.
They all look big aircraft, and by big on our route, that means 737 or A320.
Yep.
And in this case, I'm seeing one of the aircraft almost, well, you know, a fair way into Bass Strait.
Yeah,
Although,
halfway across at least.
Yes. So this is
Wow.
This is actually able to detect 3 different aircraft and the tropo scatter. I'll just mention the difficulties you're up against in separating the aircraft. Because you're using an FFT function in Spectrum Lab to narrow the bandwidth.
Yep.
If you say want to use a bandwidth of 100 millihertz,
Yep.
it takes 10 seconds. It averages everything over 10 seconds.
Okay.
And of course, if the Doppler is changing, then you tend to smudge 10 seconds into the next 10 seconds.
Yep.
Now I've chosen to actually use 200 milliseconds, which is about 5-second averaging.
Okay. Okay.
But even 5-second averaging does sort of spread one part into the next, even if it's only moving slightly.
Okay.
But often it's worth, if you see something interesting, playing around
With the parameters. Yeah.
and getting the best out of them. So that's the 432. Well, now
I agree with you. They're remarkably similar.
that's right.
They're just okay.
Now, when you go to 23 centimetres, you actually can get more gain. We sort of had about 15 dB gain on 23, but on 23 the maximum gain was up to 30 dB stronger than the troposcatter. And you can see the troposcatter now is almost invisible, but if you look at 1000 hertz, you can sort of see that there is some troposcatter there.
Yeah. Some variation.
You see the higher Doppler shift too.
And the higher Doppler shift. The problem with, which we'll go into a bit more later, is as you go up in frequency, you get more forward scatter gain, but you get narrower beam width.
Okay.
And so if the aircraft's not right on the path, you don't get as much.
Yep.
And so what this is really telling us is the aircraft got closer and closer to the path, and the signal strength went from 10 dB improvement to 30 dB improvement. So while 23 centimetre sort of works better, at least on this sort of path where you haven't got them flying right on the path, 432 is better. Well, more consistent, right?
But if you then went portable and you could actually make it right on the
path, yes,
you're getting phenomenal gain.
It's probably worth mentioning a bit of history at this stage.
Ooh, some history.
Yes. The first people to report in AR about what they called aircraft enhancement was Doug MacArthur 3UM and Gordon MacDonald 2ZAB.
Okay, yes.
Now,
that was both of them.
Well,
I've met both of them.
You couldn't meet either of them anymore.
Oh, not anymore, no. But in
now they
Gibbs
found
took a long time ago.
They started. This was on 2 meters. They started doing some tests between Melbourne and Sydney. It's about 700 kilometres, so it's a long path.
Yep.
And they noticed every now and then the signal improved. And basically the stopped. Gordon MacDonald won't use digital, or didn't use digital.
Yes.
So they must have been using SSB.
Okay.
And they sort of had a weak SSB flutter in the noise, and then every now and then it'd peak.
Okay.
Now they did a bit of work on this and found these peaks occurred when an aircraft crossed the path, and the advantage they have between Melbourne and Sydney, there are quite often much larger aircraft than fly between Melbourne and Hobart.
And can I say probably a lot more of them?
And a lot more of them. And so they wrote up what they had found in AR in the 1980s, and because they were comparing troposcatter and aircraft, they defined this as aircraft enhancement, sort of the enhancement of the aircraft over the troposcatter.
Yep.
The actual mechanism in physics is aircraft scatter, which, if you're talking what's the propagation method, it's really aircraft scatter.
Yep.
But they did a pretty good job of this. And admittedly, they both had 4 Yagis, probably 400 watts SSB, and so forth. Only later I've written up the whole how aircraft scatter actually works. In those days, there was a whole lot of debate about whether it was reflections off the undersurface of the wing, the ionised gases behind the jet aircraft, and
Like a meteor trail.
like a meteor trail.
Yeah, yeah.
But it isn't actually any of those things. But the mechanism was written up really back in 1958 by an American physicist,
Okay.
and we'll go into that a little bit later. So
Okay.
we'll go to the next slide. Now, that's that aircraft. The previous slide suggests there might have been another aircraft in there somewhere, at least for part of it. So
Okay.
with that, we'll go to the next slide. Now, this is 2 meters, and you can see now in this case, there's actually the frequency is not exactly on 1,000 hertz, and that's because Brodie's 2 meter rig was not GPS locked.
Right. Okay. Drifting.
Well, it wasn't so much drifting as just wasn't on frequency.
Right.
You can sort of see that on the left side, and we know that on either of these paths, the most left is going to be the troposcatter.
Yep. Okay.
And you can sort of see the troposcatter, which I tried to pick out by fiddling the
Settings.
the
Yeah,
settings,
yeah.
996 to 997.4 and 997 to
It's pretty amazing that you can do that.
yes.
Anyway.
Well, you might fiddle for a quarter of an hour
Right.
to do this.
Okay.
I can't guarantee that I've separated them completely,
Right.
but you can see that on the right-hand side there is a weaker aircraft.
Yep.
In the middle there's a stronger aircraft that started off pretty close to the troposcatter.
Yep.
And the end result of this is the light blue line is the aircraft scatter, the red is the troposcatter, and you can see how jerky that is,
yeah.
which is
Much greater variation.
which is like what troposcatter is.
Yep.
And the dark blue is
Another one.
another aircraft, but weaker. Now that could be a very small aircraft or
Off the path.
off
or
the
something,
path
yeah, okay.
and so forth. But once you get down to 2 meters, the amount of Doppler shift is starting to get so low that it's very hard to
To pick the difference between the two of them. Yeah.
But, so
Okay.
and between an aircraft and the troposcatter, we're not looking more than 2 or 3 dB.
Yeah. Okay.
We'll go to the next slide. Now this is the aircraft in this case, and I suspect the aircraft over Devonport was the strong one. The aircraft that just left Launceston was probably the weak one, but it's very hard to know.
There's quite a few aircraft actually on the.
That's right, and it's
Oh,
unfortunately I'm not allowed to just turn the aircraft on and off
Oh,
to
Why not?
simplify my understanding. Okay, now I did a lot of not a lot. I did some tests with Brodie on 6 meters, and I got absolutely nothing on either troposcatter or aircraft scatter.
why do you think that was the case?
I think there's a number of factors. Our antenna gains are much lower at 6 meters.
Yep.
We're only using 4 elements against 10 elements.
Okay.
Noise levels are generally much higher at 6 meters than they are at 2 meters.
Yep.
So
Okay.
finding weak signals in the noise
It's a challenge.
is a challenge. and I couldn't get anything at all on either.
Okay. Okay.
And I think the other factor is that you get a ground null depending on the height of your antenna in wavelengths.
Okay.
And so if you're, as I am, only got my antennas probably at about 10 or 12 meters, both 6 and 2 meters, 6 is really 3 times higher in wavelengths.
Yeah.
So
okay.
its ground null is reasonable at 1 or 2 degrees, but 6 metres, the ground nail means you don't get anything.
Okay.
So to overcome this problem, I got Peter,
Okay.
VK7 PD involved. He's got a pretty good takeoff to the north,
Okay.
not good down to the south.
Not at all.
And
You know about that, Richard?
and in this case, again we've got a non-GPS locked receiver,
Okay.
but you can see the tropo scatter because of its variability on the left.
Yep.
And the aircraft scatter, they're very close in frequency.
Yep.
And I did my best to separate them. They sort of get together at the end, and if you look at the graph between the green and the red, you'll see at the end those graphs sort of follow each other.
Yeah.
and,
Okay.
and I just couldn't separate them. But you can also see that the aircraft scatter gain is essentially zero compared to the tropo scatter. So what all this is telling us is the higher in frequency you go, providing you can have the aircraft right in the middle of the path,
Yep.
the more scatter gain you get. But the tropo scatter is falling off as you go up in frequency.
Yep.
Because the tropo is fairly strong there at Peter's place.
That's 7 dB variation on the tropo.
Yes.
Yeah. Okay.
I mean, the reality is, if you were listening on 6 metres on voice, you wouldn't know whether there was an aircraft involved in this or
No.
or tropo scatter, and it'll all be adding together in the passband that you've got.
Correct.
And the shift is 1 or 2 hertz on voice. You don't even notice.
Wouldn't even notice
Uh,
it. Okay.
So, next slide. This is the situation. The aircraft leaves Launceston and it's almost on the path. Now, you then say, well, how did we even separate the two? And I think what's happening here is because the aircraft's leaving Launceston, it's still climbing. And so we're not only getting Doppler shift in the horizontal dimension,
In the vertical as well.
in the vertical as well. And that little bit of Doppler shift allowed us to separate
Okay.
the two aircraft.
Okay.
Now, at one stage we're playing around on 432 and Brodie must have had his waterfall pretty wide. In fact, he tends to just watch on a WSJT waterfall.
Okay.
And when I replayed it, he says, oh, the aircraft's down about 900 hertz, which we hadn't seen anything like that.
Okay.
You can see the tropo scatter there at 1,000 hertz.
Yeah. Nice line.
It appears that there's a weak aircraft going through there, and then another aircraft that's almost died. So we then looked at the Flightradar to see if there was an explanation.
Okay.
And next slide. It's a bit hard to see, but
So, there's a Hobart to Melbourne flight,
yes.
which is a Jetstar flight, and then there is a Virgin Hobart to Melbourne flight.
And if you look at
and
the
they're
blue,
10 minutes apart.
yes, and see the
Oh, they do a big turn partway, about 2/3 the way across Bass Strait. Ooh. Oh,
that
this is
change
the
of
one
course?
that
that
this
generated
is
the large
correct.
Doppler shift.
Okay, so this is the one you said they probably had traffic or something and diverted them off to go for a bit of a Cook's tour.
That's right. Well, they
Okay.
slotted
Okay.
them into the the landing positions in Melbourne.
what do they call it? The big hayride? No.
Well, whether they went for hayride, I haven't checked, but I think they just diverted them off and then told them to come back.
Yeah, it's time back in here. Well, there you go.
Yes. So we'll now look at a bit of theory to explain what happened. Unfortunately, I think this version of PowerPoint
changes things around a bit.
Changes things around a bit. But what I'm trying to say is the forward scatter gain is proportional to the frequency squared.
Okay.
And that was written up in 1958 by Professor Siegel or something.
Yeah, K.M. Siegel. Yeah.
Now he did this as a very simple thing to demonstrate it. He just assumed that we're dealing with a sphere.
Okay.
Because it was just a theoretical thing.
Yep.
And he looked at the relative signal that is scattered back from the sphere compared to what is scattered in the forward direction.
Okay.
Now, you can easily see that what is scattered back, providing the wavelength is small compared to the size of the sphere, will basically go in all directions.
Right.
Well, all directions back,
yes.
but from 90 degrees either side of the sphere, but coming back this way.
It's all back.
And if it's spread that way, there's very little gain.
Okay.
But on the forward direction, you are actually blocking the wave because the back scatter has no longer has effectively blocked that part of the wave.
Yep.
But there's still a wave front going forwards on either side of.
So around the sphere.
Well, it's going
past the sphere.
Past the sphere.
Past the sphere.
Now, a Dutchman named Huygens.
Yes. Okay.
Told us that waves, when you block them, because if you're in a plane wave front, they're all cancelling each other out and moving forward.
Yes.
But if you block it in the middle, then they will move together.
You're correct. They'll converge past the object that it's going past.
And he worked out that the scatter gain is proportional to, well, he actually worked it out, it's proportional to the square of the area and the square of the frequency. Now, that means every time you double the frequency, typically between 6 to 70 and 23, you're going up by about a factor of 3.
Yeah, okay.
And if you square a factor of 3 is 9, and then you say 10 log 9, you get actually about 9.
Yeah.
9.5.
Okay.
In log terms, gain in going up. So in going up in frequency, and what I've done is in this table, I've used 6 meters as a reference, and you can see I go up about 9 dB each time. And so the forward scatter gain goes up from 9 dB, 18 to 28 by the time you get
to 23
centimetres.
Yeah, well and truly.
Now, the troposcatter, on the other hand, there's a formula there for troposcatter. There are various authors who have slight variations on the troposcatter formula, but they all agree on the 30 log F term, which is the frequency variable term that we're interested in.
Okay.
Now, the 30 log F term comes from 2 factors. The normal 20 log F is the free space losses that result from the fact that losses are all determined with respect to antenna gains, which are the isotropic antenna gains, or the gains over an isotropic. And isotropic antennas have a capture area It's much larger at 2 metres than it is at, say, 23 centimetres.
Yep.
And so the capture area, in fact, goes up as the square because it's in 2 dimensions.
Okay.
The capture area goes up as the square of the wavelength. So that's 20 log f, and the remainder of that 30 log f, I said that the wrong way around, but I think people understand. The remainder of that 30 log f is 10 log f, and what that's saying, the tropospheric losses are increasing, so it's going negative at about 4.5 dB each time we go up 3 dB.
Yeah. Okay.
So as you go up in frequency, your scatter gain is going up and your troposcatter is going down.
Yeah.
And that's sort of roughly what we saw from these tests.
Okay.
The end result of that is you go from 6 metres to 2 metres, 13.8, 70 centimetres you're going 28, and 23 centimetres you're going 42 dB over troposcatter.
Yep.
And that sort of shows you that we could hardly see any bloody troposcatter
At 6.
at 70 centimetres.
Yeah.
We
okay.
could see a good tropo at 6.
Yep.
But our aircraft scatter went up dramatically as our troposcatter went down.
Yep. Yeah. Okay.
So to put that into a slightly different context, what I've done is, based on the actual experimental results, I've compared just 2 metres 70 and 23 because
Yep.
the 6 metre results we got were from PD, which is different distance, so
Yep.
we can't use those.
Okay.
But essentially, the difference based on this theory should have gone up from 0 to 14 to 28 dB.
Yep.
And the examples went up 0, 12 to 27.
It's pretty close.
It's pretty. Now, given that there are lots of other factors, such as whether the aircraft's lined up and so forth,
Yep.
it's almost too good to be true, but it does demonstrate.
Some experimental variation.
Yes.
Yeah.
Now, if we go to the next slide, the other problem when you go up in frequency, you get all this gain, but the beam width narrows. Now,
Don't get something for nothing.
you don't get something for nothing. But what is interesting is, fortunately, planes are not quite the same as spheres.
Correct.
They
More
have,
cylindrical and long.
well, front on, the body is equivalent at blocking the wave equivalent to a spear.
Yeah. Okay.
But then you've got these wings, and the wings are very large in the horizontal dimension. So the wings produce, they don't have that much area compared to the body, so they don't block as much wavelength. So they produce a very narrow, high gain beam, but because they're from a small area, they're not so strong.
Yep.
And the body produces a wider beam width, and because it's larger, it's stronger. But in some situations, which we'll go on to at very high frequencies, even the beam width, like 10 gigs, even the beam width of the body is so narrow that it never gets back to the ground, and this diagram
Okay.
shows what's happening. Now, the thin wings have a very wide beam width, and when you get up to 10 gigs, what happens is the wings may be at any particular point in phase with the body or out of phase.
Yep.
And so as the aircraft goes past, they'll all be in phase if it's absolutely right in the middle.
Yep.
But if you're off to the side, you will see as it's moving, the signal strength going up and down.
Yeah.
We don't seem to see much of that, although we did see the signal strength dropping off at 23 centimetres. But the thing that actually seems to happen is that while you've got to use, when you go up at frequency and you get this enormous gain, you also get side lobes.
Okay.
And even though these side lobes might be 20 dB down, because you're dealing with a main lobe that might be 60 dB up, they're still quite good.
Yeah, yeah.
But they're competing with the wing lobes.
Yep.
So
It's a fairly complex surface.
That's right, and that's why probably Professor Siegel decided to analyse a sphere. Now, I actually spoke to a ham who works at a place which he probably doesn't want me to say where it is.
Okay.
But it is possible in this day and age to buy computer programs that can actually analyse the complex shape of aircraft and look at all of these scatter lobes. Now,
Wow.
This-
Okay.
this is important when you're designing what is the new
F-35s.
F-35s.
Yeah. Or stealth bombers.
Yeah.
Yes.
Now, what they're mainly concerned about is they're flying in towards a radar.
Yep.
So they're mainly interested in getting the backscatter down as much as possible.
Yep.
The reality is, though, they've still got a whole lot of engines and things inside the aircraft, even if it's a carbon fibre
No, correct.
aircraft.
Correct.
So, in the forward scatter situation, you're still going to block most of the energy, and in the forward scatter situation, it's going to be pretty visible.
Mm.
The Russians, I read about when I started doing this 10 or 20 years ago, had built a ring of forward scatter radars to detect anything that was coming onto their territory from Europe. I suspect they're looking at improving those.
Correct.
So this is an active field where
I know well and truly. And it's interesting. It's interesting you say that about the Russians. It was a Russian paper. This came from Skunkworks. So there's a book written by the guy that actually ran Skunkworks, which is the aircraft manufacturing facility that produced the stealth bomber. So, and he talked about the fact that because they were part of the Air Force's almost in a circle from the point of view, they shared a lot of papers that foreign papers that were actually being translated, and there was a Russian paper that talked about Maxwell's equations and the fact that there's some nuance in the Maxwell equations where they had theorized you could actually make the radar signature, minimize the radar signature.
yes,
It was only theory. It was only theory, well and truly. And so they got the brains trust together in this organisation and said, if we create this particular shape of aircraft and everything is in triangles, particular triangles, they talked about the fact they did a whole lot of work on the engine intakes and the engine exhaust,
yes,
because that was the thing that was providing a lot of the signature.
yes.
And so there is all of this work that went on. When the pilots get in those aircraft, they literally have tape that they tape up the door with.
Oh, okay. Okay.
So there is no variation
in the surface.
all the way around, and there's a whole lot of things that they do, and they talk about all of this in the to minimise the signature.
Yeah.
And it's fascinating because they talk about when they first created these aircraft, and they were super duper secret. They took them to a test range, and they took them there at night because they didn't want anybody obviously to see these things. They had the radar technician in the the container in the middle of this airfield in the middle of nowhere, and did these flights past, and they did quite a few number of these flights, and then went into the aircraft, the radar technician, and said, "Well, did you see it?" And he went,
If you've gone
"Seen what?" And so that was one of the tests that they actually had.
Yeah.
But yeah, absolutely fascinating. But it was originally a Russian
idea.
paper.
Yeah.
On how they could make things stealthy. Anyway.
Yes.
So-
Okay. Now to the conclusions. First of all, Spectradar is very useful for comparing signal levels between tropo and aircraft scatter, as we've seen. And for aircraft between myself and Brodie, we never really get the aircraft right on the path, so we never get the advantage of that really high gain.
Yep.
70 centimetres seems about optimum. 23 can give greater gains, but it's got to be closer to the alignment, and often it's not, so
Yep.
it doesn't do as well. 2 metres gives very little gain over tropo scatter on this path.
6 metres, doesn't it?
And 6 metres doesn't work at all for me and Brodie, but it does work on the shorter path. But
So that was between PD and Brodie.
between PD and Brodie.
So the angles are just different.
Yeah.
Well, the path's shorter, which helped. His takeoff angle is better than mine. And even so, there was almost no difference between the tropo and the aircraft scatter
Okay.
on that short path. So I can't imagine any situation where aircraft scatter is going to be useful on 6 metres.
Yeah. Okay.
That's it. Thank you.
Well, that is fantastic, Rick. Just stand by, because what I was going to do, I was just going to make sure that there wasn't any. There was.
I'm going to get that 70 centimetre antenna up there, Rex.
Definitely. Definitely. Live. That's what I want to do. I just want to see whether there were any comments on the streaming channel. We're working on it. That's what I want. Let's kill that. No, forget that. We've got Colin, VK5 COL, and we've got Ron Mann as well. So okay, no, there's no questions come through. If you do have any questions on the either the stream or via RF, please let us know. Shoot them into the chat, and we can pass them on. Now, just while we're waiting for that, the latest DUBUS magazine. I think that's the latest, isn't it?
Yes.
I think it is. Yes.
Yep.
The latest DUBUS magazine, which we'll be going through in a next time, has in fact the talk that Rex and Andrew Kleckerchuk gave us 2 weeks ago on more auroral openings on 2 metres with Q6515C with Mr. Rex, Andrew Kleckerchuk, Dr. Andrew Kleckerchuk, and Brodie Churchill, VK3MAP. So there's a very short little article on what we saw a fortnight ago. So there you go. I love it. I love it. So what's the next thing you're going to be doing, Rex?
I don't know.
Or are you going to continue with your or wait for the next Auroral event?
Well, Brodie's, I think I said, Brodie's up in North Queensland at the moment and won't be back till Monday.
Okay. Half his life.
But he did send me an email today with some data which is worth investigating, where Dave, VK7 DC, Bernie,
Yes.
was looking at aircraft scatter from the beacon, the VK2 beacon at Nimitabel.
Okay, yeah.
And these are large aircraft flying across from New Zealand to Melbourne.
So international flights, so
Yeah.
big planes.
Big ones.
Yep.
And as well as that, they're not. I mean, we're dealing with aircraft front on, and the projected area of an aircraft front on is not very great, because otherwise it blocks too much air which you're flying against. You try and minimise it. But the projected area that blocks the wavelength side on is much, much larger. And so,
Flying at 90 degrees to the...
well, it's actually not 90 degrees, it's 67, but you still get, even at 67, you get a fair bit of the body blocking the wave.
Okay.
And Dave had collected some data on the beacon. Now, the problem with the beacon is it's CW, so it's very hard to see exactly what's going on.
Okay.
But we think we can organise Rod 2TWR to transfer from his home station some single tones and look at aircraft's side on. Now, because the beamwidth will be very narrow and they'll be getting through the path very quick, we expect very strong signals, but for not very long.
Not very long. Okay. I was also just thinking then, what about the Air New Zealand flights between Hobart and Auckland?
Auckland and Perth. One that flies overhead here.
Yes. The trouble is, even that, the max, even at sort of 33 or even 38,000 feet, Brodie can't see those aircraft because of Earth's curvature.
Yeah, okay. So what sort of maximum distance are we talking?
To the aircraft, well, an example that I remember is that you can see an aircraft at 38,000 feet, assuming you've got a 0 degree takeoff, out to about 433 kilometres.
Okay.
Wow.
So if you want to do, say, a 960 kilometre path, you've got to get the aircraft flying absolutely in the middle.
On the path.
and
have two stations that are on the path.
And ready to go for a
and
very
that
brief,
distance apart.
brief moment.
Yeah.
Yeah, okay.
Now, Dave HZ and I did do a 10 gig aircraft scatter contact at 910 kilometres using an aircraft that was flying Melbourne to Cairns, which we both lined our
yourselves up right on the path.
Yes.
Yeah, I remember that. But you did a talk here about that.
Probably did. Yes. Getting back a long time. About 10 years ago, at least. Yes.
That's pretty cool.
Now, you can sometimes do a bit better if there is increased refraction in the lower atmosphere.
Okay.
And that, I mean, those figures I quoted you are based on the standard 4/3 rule.
Yeah, yeah.
But you can get a situation where if you don't want a strong duct, because a strong duct will
grab it and spit it out somewhere else.
That's right. But you can get a situation where it's not really a duct, but the refractive index is helping.
Okay.
And you can, there are hams who claim to have got to a little over 1,000 kilometres, just being very lucky. Yes.
So it's tropo and aircraft enhancement,
No, that's with aircraft scatter.
right. Okay.
They wouldn't be getting any tropo at that distance, no.
But a refractive layer enhancement.
Yes, that's right. It's
Sorry,
quite
not tropo. That's the
yeah,
wrong
yeah.
terminology.
It's quite different to tropo scatter.
Yeah.
It's just that the refractive index of the atmosphere bends it a little bit more.
And assists.
Now the 4/3 rule, which is commonly used as a typical refractive index, means you get another third from what you would get for line of sight.
Yeah. Okay.
Or in a vacuum.
Yeah.
And it appears there are occasions where you can do a little bit better than that with refractive index.
Okay. Fantastic. Well, that's excellent. Thank you, Rex. Absolutely fascinating. Absolutely fascinating. And these are our bands. These are standard flights. So if you find yourself on the path,
and with a good takeoff, and the
an unobstructed takeoff,
and the other guy on the path with a good takeoff.
Correct. So,
I mean, mainly I can't do much better because of my takeoff. Between Brodie and I, it's only 505 kilometres. I can see a VK3TE who's probably at about 620.
Okay.
Who's got a very good takeoff, and he's a bit further to the right, so I come a little bit down the side of Mount Non-Lochte.
Okay.
It means I'm not on the central part of the forward scatter lobe, but have some signal is better than none.
Correct.
But I think anyone who's got essentially less than 1 degree takeoff, it's worth looking at what your options are. Yeah.
Okay. Fantastic.
Those of us that had 4 degrees, let's not worry about it.
Well, you said you were getting some.
Yeah, I was getting a few, but they probably were aircraft scatter ones. Should leave it on more often, I think.
Yeah.
Gather some more.
Yeah.
Okay.
Some more data.
Okay. Well, we'll wrap it. What are we talking? Oh, it's 8:30. Okay. We'll. Okay. Hang on. Colin. So this is VK5COL. Have noticed sometimes when the RFDS, so the Royal Flying Doctor Service, Pilatus PC-12 come into land at the town airstrip, you sometimes get a signal boost for some of the longer distance repeaters for a few seconds on 2 metres. So there you go. So where are you, Colin? Just let us know which town we're talking about. That would be good. It's obviously a town that's serviced by the Royal Flying Doctor Service, which, can I just say, so is Launceston, because that's where the RFDS base in Tasmania is. So there you go. Excellent. Thank you for that, Colin. That's only a little plane too.
Yeah.
That's
you do get providing you can both see the aircraft.
Yep.
You get an advantage of having the aircraft closer to one end than the other.
Yep.
Because the signal is dropping off as inverse square to the aircraft and then inverse square to the other end of the path.
I know where he is. He's in Yorktown.
Oh,
which
right.
is on York Peninsula, in the middle of York Peninsula.
Yeah.
So roughly 80 kilometres west of Adelaide, Yorktown on PF84TX.
Right.
Lots of jets go over, yes. And that'd be international jets as well, up high.
Adelaide to Perth, yeah.
Yes, yeah.
Although, or one's perhaps Melbourne to, because Adelaide won't have gone up to full height.
Correct.
Yeah.
Oh, good stuff. Fantastic. Thank you for that, Colin. That's excellent. All right. Well, we might call it quits at that, and there'll be another program, same time, same frequencies next week. This has been VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our DATV experimenters night. And thank you to Rex for sharing, and Richard for coming along.
Thank you very much.
Thank you. And we'll see you again 7:30 Wednesday Eastern Standard Time on streaming and also RF around the Hobart area. So we'll bid you farewell. 73. Have a good rest of the week. Now here we go. Here we go. Oh, there we go.